Next, we look at limits of infinity. In particular, I want to look at some examples and try to draw some conclusions based on specific examples. We've already discussed this one a little bit. The limit as x goes to infinity of 1 over x equals 0. And you can see if you graph it, you'll see that the function comes in and does something like that. And we know that it becomes closer and closer to the x-axis as x goes to infinity. I'd like to quantify, how do we know this limit is going to 0? I mean, what's the definition of this? You have other functions that might do something like this. Instead of actually go to 0, they may do something like this weird stuff, but then they might smooth out and approach some sort of a horizontal asymptote as x goes to infinity. Something along those lines. Well, the definition looks like this. Get this errant stuff off of here. This means the limit as x goes to infinity, f of x equals L, means that for any epsilon greater than 0, there is n in R. When I write that, I'm just saying that n is a real number, such that x greater than n implies that the absolute value of f of x minus L is less than epsilon. So if you look at our example that we have, let me actually prove this limit. Prove the limit as x goes to infinity 1 over x equals 0. X equals 0. We're looking at this quantity, 1 over x minus 0. And that's the thing that we want to get to be less than epsilon as we allow x to become very large. Now, since I'm dealing with positive numbers, x is going to positive infinity means x is going to be positive from some point out. I can simply work with 1 over x. And now, how would you think you'd get it to be less than epsilon? In fact, what would you use? Well, if you look at just trying to solve this thing, I get an idea. If I want 1 over x to be less than epsilon, I can multiply both sides by x. And since epsilon is positive, I can divide by epsilon. And all this work doesn't change the inequality sign because everything I've worked with has been positive. So in fact, this could be the n. So, well, 1 over epsilon. Then, if x is greater than n, that means that x is greater than 1 over epsilon, which implies that x epsilon is greater than 1, divide by x, that implies that epsilon is greater than 1 over x, which is precisely where we wanted to get to. Now, there's so many complications here. I don't know how much I want to go into heavy epsilon delta stuff with this. I'll explain. Let me do the next one. I actually would like to prove this. The limit as x goes to infinity of 1 over x to the p over q equals 0, where p and q are positive integers. So I'm talking about rational exponents here. P over q would be a rational number. So if you play the same sort of game, we'll be looking at stuff like this. 1 over x to the p over q minus 0 is less than epsilon, is where we eventually want to get to. Since x is positive, I have 1 over x to the p over q. It's less than epsilon. Now, how you try to actually get x by itself here in some way, shape, or form. So what I would probably do next then is take both of these, p over q, take both of these to the q over p power. Now, is this a valid statement? I mean, does that inequality stay the same? Does it change or does it stay the same? Well, the fact is it does stay the same. Because when you're working with p over q, the graph, if you look at x to the p over q, many times it'll resemble, depending on what kind of a number this is, but many times you'll resemble something like this. And in fact, I believe I indicated at one point that that quantity is going to infinity as x goes to infinity. So, note that the limit as x goes to infinity, x to the p over q equals infinity. This, I don't think I've proven that yet. The problem here is this step. This is the thing I want. How do I? The key lies in the shape of the graph. If you look at this, say I have an x value, and then to the right of it I have another x value. So what I have here is clearly x1 is less than x2. If you go up to the graph and find their y values, this, I'll call this one y1, and the one corresponding to x2 I'll call y2. Notice that y1 is also less than y2. In other words, I don't have to change the inequality because this original function preserves less than or greater than. Since x1 is less than x2, y1 is less than y2, that's because of this graph. I suppose taking my word for it is that it will have to go. So whenever you do any kind of exponentiating, whether it be x squared, x cubed, whatever, most times, or all the time, unless you're dealing with 1, x to the 1 doesn't do, well, x to the 1, the graph itself is an increasing function also. So that even that case is fine. So what I'm saying is if you take something to the q over p power or p over q power, it doesn't change the fact that the function is increasing. So the inequality is preserved here. That gives me 1 over x is less than epsilon to the q over p. Or I can rearrange this and write 1 over epsilon to the q over p is less than 1 over x. Sorry, is less than x. Well, that is what I can set my n to be equal to. So, for that epsilon that was given, let capital N equal 1 over epsilon to the q over p. Then 1 over x to the p over q is less than, let's see now, for x, let n be that, then for x greater than that n, so x is greater than 1 over epsilon to the q over p. I can reverse all the stuff that I did before. Take both sides to the p over q. So x to the p over q is greater than 1 over epsilon, which means that when I solve this inequality, I'll get epsilon is greater than 1 over x to the p over q. So this will be less than epsilon as needed. Let's do some examples. First example, compute. Now I'm going to do these without a calculator. I may use a calculator to, well, I don't think I'm going to. I'll let you do the checking on that if you'd like. Let's look at the limit as x goes to infinity of 2x cubed plus x minus 4 divided by negative 5x plus 7x cubed. Let's see where this leads us. The trick with this is the following. I'm going to factor out the higher of x that I see in the numerator. In that case, it's x cubed. What that leaves behind is 2 plus 1 over x squared minus 4 over x cubed. In the denominator, the highest power also is x cubed, so I'll factor that out. And that'll leave me with negative 5 over x squared plus 7. Now I can cancel the x cubes. If you will, this is kind of like canceling out the whole in a rational function. Now I can directly do each of these. Remember, constants are unaffected by the limiting process. This is 1 over x to the something, so that makes that a 0. Negative 4 over x cubed is also 0. If you have 4 times a number that's diminishing to 0, 4 times that number is also doing that. I'm not going to go through all the details. I'll just try, hopefully you'll buy these as I'm doing them. Negative 5 over x squared goes to 0. Plus 7. I can put a negative in front if you want. It really doesn't matter. In the end, I'm left with 2 over 7. Graph this thing, check it out. See, make sure that it actually does what I said it does. Another example. What about the limit as x goes to infinity, square root of 1 plus x squared minus x? Now this is the one I cautioned you before to not write something like infinity minus infinity. The trick is to multiply by the conjugate. So I'll multiply it by the square root of x squared plus x. Let me make it so I do the same thing to the numerator and the denominator. And this other fraction, I'll call it a fraction because I'll write it as over 1. But when I multiply this out and I do the FOIL method, you'll remember that the intermediate, the middle terms all cancel out. And I'm left with the square root of 1 plus x squared minus x times x, which is x squared. And the denominator still has 1 plus x squared, the square root of that, plus x. Of course, squaring a square root makes it disappear. I get 1 plus x squared minus x squared divided by the square root of 1 plus x squared plus x. X squareds cancel out, and I'm left with the limit as x goes to infinity, 1 over the square root of 1 plus x squared plus x. This may seem strange, but from the denominator, I'm going to factor out the highest power of x. And I think it might be beneficial to do it in 2 different places. You can see that x is the highest power here, but if you look at this, x squared is the highest power under there, but it's fooling you. If I take out an x squared inside of there, I'll be left with 1 over x plus 1 plus x. I can factor out. If you factor out x squared, you get the limit as x goes to infinity, 1 over of 1 over x plus 1 plus x. And now you can see that I can factor out an x. So that'll be the limit as x goes to infinity, 1 over x times the quantity, square root 1 over x plus 1 inside of the square root, and then plus 1 outside of the square root. This is the limit as x goes to infinity. I think what I'll do here is use my limit rules. Some of them actually do work. As long as these limits both exist, you're okay here. All right, so let's throw these in. Well, I already know the limit. All right, so let's throw these in. Well, I already know the limit as x goes to infinity of 1 over x is 0 times this limit over here is 1 over the square root of 0 plus 1, which equals 0 times 1/2. So that equals 0. Check that out on your calculator. Graph that thing and see what happens. So that's the trick with those things. I'll do one last one. I don't know why that was a bad choice. Let me do one more. X goes to infinity. This time let me do the square root of x squared plus x plus 1 minus the square root of x squared minus 3x minus 9. And I'll do precisely the same thing. I'm going to multiply by the conjugate. So I'll get the square root of x squared plus x plus 1 plus the square root of x squared minus 3x minus 9. And I'll divide by that same thing. Of course, the other fraction, if you need the help, you can think of it as all being over 1. Same deal as before. Difference of squares formula will allow you to just work the outer, and the OI of FOIL all cancels itself out. So what I'll have then, if I square this first piece, if I square that piece, I'll get x squared plus x plus 1. Now be careful here. My students do this mistake all the time. You need to put this next thing in parentheses. X squared minus 3x minus 9. And in the denominator, I'm going to get the square root of x squared plus x plus 1 plus the square root of x squared minus 3x minus 9. A lot of stuff cancels out here, so let me go ahead. Actually, not as much as I thought. The limit as x goes to infinity. The x squareds cancel, which is the important thing. I'll be left with 4x plus 10 divided by the square root of x squared plus x plus 1 plus the square root of x squared minus 3x minus 9. Let me increase vinculums to account for all these things. Now once again, as before, I'm going to factor out the largest power of x from the numerator that I can. So in this case, it's just x to the 1. That'll leave me with 4 plus 10 over x. And in the denominator, I'll do the same thing as I did before. I'll pull an x out of each of these. Remember, that's because it becomes x squared once it's inside the square root. Now, I don't have to do an absolute value of x because x is going to positive infinity. And now I'm ready to just plug in well, not quite yet. One last step, just to make clear what I'm doing here. I have an x times 4 plus 10 over x in the numerator. And then I have an x times the square root of 1 plus 1 over x plus 1 over x. I was a little too fast on that. Let's get this out. Plus square root of 1 minus 3 over x minus 9 over x squared. Now I'll cancel out my x's and I'm ready to put in the numbers. So I know that the 4 will stay a 4. 10 over x will become 0. In the square root, you'll have 1 plus 0 plus 0 plus 1 minus 0 minus 0. That gives me 4 over 2, which equals 2. one last thing before I finish this up. Had I done this limit, but instead made this piece be negative infinity, let me copy that. These two lines I want to copy. Now, for some reason, they'll come in real thick, but it doesn't matter. I want it. So let's take this and copy it. Notice it's thicker, but that's not egregiously so. If this had been going to negative infinity, down here, then these would have to have been the absolute values of x. And then the absolute value of a negative number is the negative of this number. So you would have had to rewrite this as the limit goes to negative infinity, x times 4 plus 10 over x, divided by negative x times 1 plus 1 over x plus 1 over x squared, plus the square root 1 minus 3 over x minus 9 over x squared. With that in mind, now when you do your canceling, it's not straight up canceled. You have that negative to account for. So what we end up in the end is not 2, but negative 2. So check that out. Make sure you do all the steps. See how it works out. And again, I challenge you to check all of these on your calculator.